So I'm also recording. Welcome to our Signals and Systems class for the spring 2021 semester. Uh, Probably you all know me, but I'm Gözde Ünal. I'm your instructor for this course. You have two TAs, teaching assistants. I believe they will be joining soon too, Yusuf and Fırat. We will go through the syllabus soon. But first of all, I want to motivate you by asking how do you think you hear my voice currently, right? I mean, why are signals and systems important? Why is this some topic or some subject that you should really know about, or at least have some fundamental knowledge about, as a computer engineer, by the way. Uh, I mean, the signals are everywhere, right? It pervades our lives, like you're speaking to your friends all the time. I mean, like, again, my speech reaches you all through all kinds of signal transmission and signal processing. You listen to music, for instance, right? Online, maybe Spotify. All kinds of signal processing is going there on there. Images are video signals, like when you watch TV. Those are all signals. Broadcasting of signals, communication. By the way, communication is one of humankind's most probably differentiating, discriminating feature, right, from other beings, like advanced communications. And actually, signal processing was really advanced during World War II. I think you guys would guess this, right? This crazy war between Germany and the Allies. There was all big race actually in terms of radar signal processing, in transmission of signals, encryption, also computer science, of course, right? In terms of algorithms and computation, efficient computation, for decryption, encryption, decryption, for signal jamming, for instance. Signal jamming was trying to broadcast signal at the same frequency that your opponent, your enemy, is broadcasting to, in order to jam their communications. I mean, all of these things rely on signal processing, and even further, actually, more closer to you in your biological life being. Your body, it consists of a lot of biological signals. Currently, your heart is beating like maybe 60, 70 times per minute. And we measure those signals, for instance, to monitor the health of your heart. Your brain signals, like how information is transferred in the brain fibers. For instance, we can try to understand those things through magnetic resonance imaging, some special kinds of magnetic resonance imaging. We try to, for instance, again, measure the health of the lungs, especially with this COVID disease. I'm sure all of you have heard of X-ray, chest X-rays, chest CT, computed tomography. Probably nobody would say I didn't hear anything like that, right? At this point, you all know about these medical scans. Those are all signals. X-ray, for instance, is being transmitted through the body, and it gets attenuated through the lungs when it's transmitted. And some both normal and abnormal, actually, pathological tissue or structures then could be imaged through those X-ray signals or measurements. Okay, so those are really all kinds of different kinds of signals you can imagine. Let me maybe share my screen. We can take a look at, not this one now, but I had another slide here. Let's go to here, guys. Let's open the this mode. Okay. So, okay, we said we are here together for our BLG354E course. Okay, I had some more motivational video to show you. Maybe let's watch this one. Let's see.
Don't you see it was Orville who buried the crowbar in the crypt, not the Leon burger? Don't you see it was Orville who buried the crowbar in the crypt, not the Leon burger?
What's a Leon burger?
It's a big dog.
Did you guys leave a window open when you recorded this?
You got a problem with that? I'm doing a murder mystery, only there's too much wind noise, so we have to redo a key line. But this isn't about Leon burgers or murder mysteries. It's about signals and computers that learn. But you knew that from the title.
Just for fun, read it completely flat.
Don't you see? It was Orville who buried the crowbar in the crypt, not the Leon burger. Brian King was an intern when he helped develop this automatic dialogue replacement program that fixes the wind problem and my purposely crummy read beautifully. Brian's software will make my voice match the original read exactly. Normally this would take you hours to match, and it still wouldn't be very good.
I heard that.
Car scene, take one.
And action.
Don't you see? It was Orville who buried the crowbar in the crypt, not the Leon burger. Very impressive. So what role does signal processing and machine learning play in this program?
So it's really a two-step process. With the signal processing part, we're taking these audio signals, so your speech, and analyzing it in such a way that we can figure out the important parts of the signal. And then the machine learning part is aligning those features kind of every step in time. The coolest thing is being able to do things that have previously been impossible to do and no one's been able to do before. It's a little bit like magic.
Brian told me about another application of signal processing and machine learning where instead of using sound waves, they're using brain waves. Xin Zhang is trying to tell the computer to move this arm brace using his thoughts. What are you thinking about to make the arm move?
Just grasping my hand.
Grasping your hand,
Yeah.
and that allows it to bend.
Yeah. Yes.
He doesn't have to grasp his hand, he just thinks about doing it. There, that's not him moving his arm. That's the arm brace receiving his brain signal from the computer. Xin Yi Yang heads up this brain-computer interface project. Why do you choose to use the action of grasping to move the arm?
Studies have shown that if you imagine a hand movement, it will create some very distinct changes in the EEG signals.
And how does signal processing play into this whole thing?
First, we can use signal processing methods to analyze the signals to look for specific patterns that occur when you perform a movement. Another very important application is to remove noise from the brain signals. The third one is to extract important information from the brain signals. The machine learning will try to distinguish different brain patterns. It will be able to distinguish whether the person is imagining a movement or he is resting. We can use this technology to help people with limited mobility to operate certain devices, for example, a prosthetic hand or a wheelchair or a computer. If you can't use the keyboard, you can use this technology by using your brain signals.
There's another recent development that couldn't exist without signal processing and machine learning.
What do you do for fun? ¿Qué haces para divertirte?
Li Deng and the team at Microsoft came up with this translator. With this, he spoke with me in his native Mandarin. What's been the biggest challenge in creating the Skype translator?
最大的挑战是实现高精度的语音识别和机器翻译。
The biggest challenge is to achieve high-precision speech recognition and machine translation.
语音识别是一个核心的信号处理的问题。
Speech recognition is a key signal processing problem.
将机器学习应用到语音识别， 精确度大大提高。
Machine learning has been applied to speech recognition.
Okay, so I hope that really motivates you. Were you able to follow what is happening there, guys? Like in the first part, there was a noisy video, right? With the noisy actual speech part, noisy sound part, because window was open. And signal processing and machine learning engineers was able to really record that woman's voice in a studio environment without noise and align actually the noisy version, right, of the noisy speech, this, because she's saying the same sentences, and the clean speech signal. He aligned them and then he actually inserted into the video. I can't. Oh, just a sec. Okay, so maybe actually we could see the others later, some of the motivational video, but I will today do a short course. Okay, so first we talk about what is a signal, then what is signal processing, and then what drives signal processing. Actually, it's both mathematics and models because language of signal processing is mathematics. So this course will be a lot of mathematics. So I have to tell you, and you guys already are computer engineers, so or becoming computer engineers, so you know the importance of mathematics for us, right? So, so a signal is actually a quantity that carries information, and it has an independent axis, like for instance, carries information over time, over space, over some dimension, right? And signal processing is manipulating those signals to extract some information. And here in this course, the most important information is the frequency, okay? I will show a graphics equalizer example. So first, what is a signal? Let me give you some example signals. This is what do you see here actually? This is as the name of the graphic, axis of the graphic says. This is the temperature in degrees Celsius, and this is average temperature at the Earth's surface over the years. I think this is an important graphic. That's why on purpose I put this one. Let me open your chats. Yes, Bertu, you're right. Signals are data. So it's like data processing. Exactly. Any kind of data. Okay. Right. Let me continue. All right. So, for instance, looking at this graph data signal, you can say or see the pattern. We're trying to capture patterns, right? Because our goal is to understand what is happening in the world, in the universe, around us, in the society. So that's why we try to analyze the signals or the data. And looking at this graph, I can tell, for instance, the temperature is increasing, okay, over the years, unfortunately. And this is due to humans, actually. Already defined it. This is, let me see, I think, okay, the same graph taken from another source until 2000s. This is from NASA. Okay, this time I'm also showing, you see this light pink is the crude measurements, and we also put a processed signal. 5-year running mean, actually that's, you guys will see it's a low pass filtered signal, okay? Low, so it's like keeping the low frequencies. All right, so here, what is important is we see the mean trends, and then we can look at a confidence interval like these gray bars here, right? That gives us some measure of uncertainty. Okay, remember your probability course. So mean plus minus some standard deviation 2 or 3. If you are out of, then you can actually here plot a confidence bar or around, right? Or envelope around this signal. And then actually you can start to see, for instance, outliers. You can start to see what is not normal in that period. And also here, looking at it globally, you see a general trend again, right? Of this increasing trend, unfortunately. And thanks to the human beings, actually, the Earth is warming. I think we already feel the effects currently. For instance, this is carbon, another related post or graph, carbon dioxide levels. It's higher today at any point in at least the past 800,000 years. This is crazy. You see, there are normal, you can say these are fluctuations. You will see, you can analyze these through frequency content of the signal. These ups and downs, fluctuations. So there is some oscillation, which is okay, somewhat, but after I think this was around probably 2010 or 2018, actually it says here. You see, this is such an outlier, the number of CO2 emissions. Again, it tells us there is something not right going on, right? You see from just a simple plot and interpretation of the signal, you can say that, okay? So I was telling you there are biological signals all in your body. For instance, we can measure them through ECG, electrocardiogram, which records electrical activity of your heart. This is an example, for instance, signal. You see it also has what we call, you can call this like a periodic signal. Sometimes quasi-periodic, meaning not exactly periodic, but somewhat periodic. And you can see this pattern, like abrupt changes and similar pattern repeating itself. We record these, and then the doctors, the experts analyze these to detect abnormalities, right, in the heartbeat. So you do see an important use of signal processing here. Another one is in financial analysis. Millions of people are trading every day, right? On the stock markets, this is, for instance, a stock market signal, S&P 500 index. This is an average stock price for 500 top companies in the Standard & Poor's index. This is called S&P 500 index, shown for the last 500 trading days. This was taken into 2015, but you can see there are both some oscillatory behavior, right? I can, for instance, when I look at this, I can pick up certain frequencies immediately, and there is also an increasing trend that's in the bias part of the signal, right? So traders, financial analysts are doing signal analysis every day and trying to predict, for instance, forecast the situation of stock prices for profit, of course. We do also forecasting for many other things like weather forecast, for instance, for tomorrow. More example signals, an image, it's a two-dimensional signal. Again, I wanted to emphasize the ice melting in the Arctics. The brain images, you see, this is an MRI, functional MRI example. Of course, movie signal, that's a time-varying signal, time-varying image. These are 3D signals, brain images. And then what is signal processing? We try to manipulate a signal to change its characteristics, or we extract information. Change characteristics is like, for instance, we try to denoise the signal, decrease the amount of noise. Okay, we may try to surpass or suppress some of the frequencies in the signal. For instance, high frequencies in the signal. That's again smoothing. Okay, we may want to extract some information. I will show you examples, and we do this through systems. So it manipulates a signal. You can think of system actually as an algorithm. Okay, as a computer science student, a system is like an algorithm actually. I mean, that I think would be very close to you. So I've already given these examples, I think, because signals are everywhere in our lives. Okay, and you guys can also increase these number of examples. So these are typical signal processing problems. Like I said, we try to eliminate noise. We try to correct distortion, for instance, so manipulate the signal into another form. We want to extract meaningful information from signals, and we want to compress signals, for instance. I mean, these are some example signal processing mechanisms, let's say. Eliminating noise. I showed you an ECG signal before. It could be noisy, let's say. Here, I think this was an artificial noise added, but it could be, this noise is an important phenomenon in our daily lives, in the measurements we make in our signals. Typically, it's due to sensor noise, like our measurement device, like the circuits, for instance, in your device, thermal noise, for instance, light variations, they create noise in our images. Weather, even weather change makes a noise actually. Like if the clouds are, now there is cloudy weather, and then before there was sunny weather, your image processing has to adapt to that because your image, photo quality, looks, appearance, all of that changes. Okay. So then your goal is to take this noisy signal and clean it and show a clean signal as in the next one here. So for instance, we may say you were taking a photo, your hand shakes, you get a blurry image like this. You may want to do signal processing and data processing, like you guys asked, to obtain an unblurred image as on the right, for instance, okay? Here you may take multiple photos. You may try to model the lens here, the effects of the focusing the lens. So you may try to undo those. For instance, you can also extract frequencies from signals, and this is done a lot in equalizer systems. I'm going to show you. But you can also extract an indirect quantity, like in radar, like the police actually does this a lot to measure our velocity of the car, of our cars. Sends a wave, a radar wave. Then our moving car, of course, it hits our moving car, gets reflected. Okay, and police just measures this change in the reflected wavelength, so frequency actually. And due to that frequency change, we know the speed of light. There is a simple relation actually that converts that change in wavelength to the velocity. Okay, so yeah, for instance, another I think example I was going to show was let me see. I see. Let me stop the share and check. For instance, how does Spotify make recommendations to you? different, of course, there are different techniques. But for instance, raw audio, let's say you take your raw audio data, that's a time frequency signal here. So you listen to different music, your friends listen to different types of music, and you can create a signal like this, input signal or data, and you feed it into a learning framework, for instance, convolutional neural network, and create a feature vector. This is feature extraction. Now, for instance, you can look at similarities of this feature vector with similarities of your friends, with other people in the database. Then the system algorithm will look at like what that close person was listening to, and will start recommending to you that person's preferences actually. Yes, Ahmet, you're right. The previous example was called Doppler effect. Okay. All right. So you guys I can share you these links if you are interested. You can check these. Okay. So maybe let's continue with this. Another actually use case for signal processing is compressing information. So for instance, I want to compress my signal to 1/20th its size, okay? So I can't really take every 1/20th sample. It doesn't work like that, right? I have to do it in a smart way. So one idea, and this was used in JPEG compression in the past, currently it uses another transform, but it was based on Fourier transform. And Fourier transform is something that you'll use a lot in this course. Fourier transform is just actually a transform that takes your signal into another domain with a certain basis. It's a Fourier basis. Those are cosines and sines actually. That is, you try to express your signal as summation of cosines and sines. It does this to your image into blocks, like 8 by 8 pixel blocks, takes the Fourier transform, and look at the coefficients. So one idea also in actual communications is we make a transform to the signal, for instance, send that coefficient only, those coefficients. So this is also, you see, a compression idea. Send out that compressed signal, then reconstruct the signal on the other end. Here for storage compression, similar, for instance, 10-to-1 compression, meaning from those Fourier coefficients, we find those that are close to zero and we eliminate them actually. We don't store them. That's, for instance, if we do that in a 10-to-1 ratio, then we have a 10-to-1 image compression when we reconstruct the signal. Same here with, for instance, a very, very large compression, 45-to-1. Of course, you start to lose from the signal. Here, the trick is compress so that you don't lose the features of the original data, important features. Okay. For instance, MPEG is a compression standard for videos. MP3 is a compression for audio files. You see, these all involve signal processing algorithms, data analysis algorithms, processing algorithms to process your data. Okay. You can also do this on any kinds of signals. This is another widely used signal processing application, graphic equalizer. Because guys, we will see starting next week, all signals have frequency content, okay? And we want to manipulate that frequency content. And this is very much visible or apparent in sound signals, right? Music, for instance. So equalizer is a way, is a tool to help us adjust gain of frequency. So for instance, if you're a musician, you know this, you can say, I want to, for instance, increase the high pitch or high frequencies in my vocalist, and I want to maybe suppress some of the bass frequencies in my drummer. You can do things like that if you played with these. I think Google Chrome had a Google graphic equalizer extension. So let me see if I'll be then playing this. A sec, guys, it's a little bit too high. Let me. So I will here, there is an equalizer extension. I will open it and we will try to see if we can, for instance, reduce the bass. Bass is the low frequencies, treble is the high frequencies.
Good grammar and spelling are important, but if you want to write
And
essays that
so we can
inspire,
keep the S. This is the equalizer. Let's see. You see, these are the frequencies. Let me see if I can. See, I'm trying to suppress some of the frequencies. I think they have some already set options for this. For instance, bass reducer. Okay, I should do it. Let me see, guys. Let me see. I think the with Drake, I was able to see better. Let me reduce the treble. Treble booster. High frequencies are boosted. I hope you can hear these. Let me bass booster. The low frequencies are increased. I hope it makes the point. Reset. So it gives you a way to. It gives you a way to, you see, adjust different frequencies, and in order to do that, you have to be able to decompose your signal, any kinds of signal, into frequency components. Okay. I hope you like Drake, by the way. Nice song. Yeah, I also liked it. So I said, let's just listen to Drake with this occasion. Okay. So guys, I think that maybe, and we can hear these tones next time. We will be studying tone, single tones. We will start with notes like single frequency cosines and sines. Okay. I think at this point, I want us to go over the syllabus. Any questions, or guys, are we up to at least a nice motivational introduction? I hope so. Okay. So let's go through our syllabus, because it's important to know what is expected of you. Maybe first I can show you the learning outcomes. We will be doing all of these. Describe a periodic signal in time domain. We will write it as a sum of sinusoids or complex exponentials, because we will create Fourier series representation. Why is it important to write? Then we will write any signal, not just a periodic signal, as sums of sinusoids. Why is it important, you think? I know it's too early to answer, but if I can write a signal as sums of sinusoids at different frequencies, then you see it will be very easy for me to pick certain frequencies and eliminate certain frequencies, do a frequency analysis of the signal. So this course really dwells on the frequency a lot, but it's an important concept in life. Many physical phenomena, probably almost everything is oscillating, nothing is almost stationary, and a stationary is a signal actually with frequency zero, right? It's not oscillating, but I mean stationary meaning, sorry, a constant signal. But everything, every signal, currently my voice is reaching to, it's through these oscillations, or like these superposition of sinusoidal waves reaching to your ear. By the way, your auditory system, guys, is a perfect advanced audio analyzer. It has all these different actually frequency band pickers, everything. So the signal, it comes as an acoustic wave, pressure wave into your ear. In your ear, in this cochlea, it is actually first decomposed into different frequency bands, and then that way, then of course it's converted into electrical signals from these pressure waves, sound waves, and then in your brain it is processed in different parts of the auditory cortex according to these different frequencies. Berktu, thank you. Signal, very good question, very good comment, thank you. I should say signals, we were going to talk about it, but you asked it heads up. Signals in the physical world around us are mostly continuous data. This is, you can think of the electromagnetic radiation, electromagnetic spectrum. Light waves are, you know, what is visible light, right? Currently, with the visible light, that's because our eyes are just evolved to be able to see that range of certain frequencies. There is infrared light, there is X-rays, gamma rays, microwaves, right? Radio waves. These are all continuous data. Also, sound waves are another category. Those are through the displacement of particles in the air. That's why they're also called pressure waves. Because as I'm uttering these words, guys, as I'm talking the same with you, I'm making or pushing some pressure pattern out of my mouth, right? And it's really actually pushing the air particles, and that is reaching here the microphone in my system, converted, digitized, of course, submitted or sent, transmitted to you through the communication channel, okay? And then how does it reach back to your ear? We will see this. There is a continuous to discrete conversion, like I said, like Berktu said. So there is also discrete time signals. So we will be studying both continuous time signals. Those are just continuous functions, right? Discrete ones are discretized functions. You are used to working with discrete functions as computer engineers. It's like a vector, an array of numbers, right? So that's a discrete data. We work with those mainly, but we will work with both types of data in this course. Of course, continuous processing, we will deal with it mathematically. That's a great mathematical abstraction. Mathematics is your language all your life, language of science. You should be very fluent with it. But typically, we are fluent with continuous processing in terms of mathematical modeling. The same with optimization, for instance. In machine learning, we write everything as if they are continuous, but then as computer engineers, computer scientists, especially, it's your job, you remember this through your numerical methods course, to discretize these signals and then to process these discrete signals, right, with your algorithms. And if needed, I was telling you how my voice reaches to your ear at the end. There is, if needed, like I said, this processed discrete signal has to be converted back to continuous signal again, right? And that happens through a speaker, for instance, where there are some piezoelectric crystals, there is some transduction going on there, and our actual discrete signals are interpolated, and then actually at that point, they are transformed into sound waves. Okay, those pressure waves, sound waves, and that's how your ear can hear them actually. You can't, we are not computers, right? We don't work with discrete data. We work with continuous data. Thank you, Berktu. Signals inherently are continuous signals, but they can be discrete signals, like our categorical signals, right? We record, for instance, companies or our all socio-economical systems in human life, we are collecting, accumulating lots of zillions of data. Those are saved in the records of companies, logs of, for instance, logs of customer behavior, right? Online behavior. Those things can be already discrete in nature, of course, right? Because somebody is making a purchase, for instance, and we record it. 2 days later, another purchase, we record the type of the purchase, the amount. These are data also we work with, okay? But here in the signals and systems course, the data you work with is a little bit different. It's mainly more like sinusoids, continuous signals, but you have to know like how to extract frequency component, frequency content, how to denoise a signal. Okay. So those will be all here, and we will, you guys should be really experts on looking at a spectrum representation of both periodic and non-periodic signals. And then we will talk about systems, linear, mainly in this course, linear time invariant systems. Algorithms are systems, okay? Mainly most of the algorithms we work with are nonlinear algorithms, like these learning algorithms, for instance, convolutional neural networks, fully connected neural networks. Those are, you can think of nonlinear systems. There could be a linear regression model you're working with, that's a linear system, okay? Some of the things in this course, the conventions, notations, they are, because this field was first developed by electrical and communication engineers during World War II, like I said, some of the things may sound like, look like they are for electrical engineers, but it's not. Like I said, as a computer engineer, you are expected to know what is a signal, how do you analyze its contents, what is its frequency content, because these all apply to, although we will be working with one-dimensional signals in this course, your life, guys, mainly, probably most of you will at some point become a data scientist. Your life will be working on n-dimensional signals or n-dimensional data, meaning some certain number of dimensions of the data, and you have to manipulate those data to extract necessary information, to pass that information, that's called perception. Then you pass that information to some intelligent processing for instance, making decisions, for making inferences. And the basic goal is, of course, to understand what is going on around us, to make forecasting, to predict things, to make recommendations and things like that. Okay. So we will come to these later. Then here's are your textbooks. Okay. Signal processing first, and then digital signal processing first by the same authors. And another good reference, Signals and Systems by Oppenheim and Minsky. Please read the course policies. Please avoid always cheating and plagiarism. Of course, disruptive classroom behavior, I mean, we don't expect it from you. We have very good students. We are proud of our students. So, but this is also very, very important, okay? Ethics. Keeping a high level of ethics in your life. Okay, so maybe you guys will be like, hey, this is important. I want to see the grading policy. We will have, starting next week, quiz every week. And you see, it's an online semester this semester. So I wanted to keep the quiz. This is more like actually trying to see whether you followed. It's just one simple question at the end of the course, typically, but don't quote me on that. It could be sometimes randomly at other parts of the duration of the course. You will have 12 quizzes. And so the first week and last week, we won't have quiz, but other 12 weeks. And we will take the 10 best quiz grades, okay? That's 25%. So it's like each quiz grade is 2.5 points, okay? We will have 4 homework assignments. These will have both mathematical problems, mainly programming homework assignments in Python. So you should be fluent in Python. The prerequisites, you see, Python is mandatory. I mean, you have more than basic, you have advanced programming skills at this stage. Linear algebra, calculus, of course, I assume you are good at those topics, subjects. Then 50%, so each homework is 12.5. By the way, we have conditions, 70% attendance, okay? I noted here. And submitted homework, average grade from 4 homeworks should be 40, okay? Then we have a final project, which is 25%. So this final project will be like 2 homework difficulty, about the difficulty of 2 homework. Sadık, I may try to, actually, this week I'm showing some slides. In the next weeks, we will mainly do mathematics. So I will be writing on my tablet, okay? So these slides are really introductory slides. I can share them if you want. But typically signals and systems course, we don't have slides. But the course, actually, now I remember, our textbook, guys, our textbook has, where is the textbook here? Slides, very nice slides. Actually, yeah, Sadık, thanks for making me remember. Yeah, some weeks, because they have very nice illustrations and drawings, I will be using them. Yeah, actually, I may use them. We can try to share the slides. For all these kinds of questions, go to your TAs, okay? For quizzes, which platform? Good point. Because this is these quizzes will be mathematical, you will have to write things down analytically. We can't do a test, I believe. I don't know if your assistants are around here, but we what they do is they upload the question to Ninova before the quiz starts. They give you like 15 minutes to solve the problem, and you have to upload. Take a photo of that 1 page. Nothing is more than 1 page. It's typically a short question. Upload it to the Ninova in time, okay, in 15 minutes. So these are your assistants, Fırat Öncel and Yusuf Şahin. Please know them well, okay, and write to message boards. They will be following. We are clear, right, with the grading policy and all that stuff. So this is our tentative schedule. Today I'm doing just an introduction. Let me see if we will start a little bit today. I may skip that part, but we will do, there won't be a quiz today, okay? We will go through spectrum representation, complex exponentials next week, Fourier series in continuous time and discrete time, LTI systems, like I said. Then we will look at impulse response of these LTI systems. So these are, impulse response is something like that defines the system. Then there will be an input, and we will convolve it with the impulse response. That is like a filter you can think of. We will calculate the output. So convolution is an important operation for this course and for your later life. Convolution operator is like filtering operation. Okay, so we do both continuous time, discrete time systems, convolution, and then look at their frequency response. We study then Fourier transform and its applications. That's it, okay? This week, guys, 10th of May week is the Eid holiday, Ramazan Bayramı. Our school just actually made the whole week holiday, which is good. So it will be like a break, semester break. I think it will be good for everybody. So you see, we try to assign all the homeworks, most of the homeworks before that, and we will be assigning the final project after that, okay? All right, so let me try to see if I have any more motivational things. Yeah, okay, there was also another nice slide set here, which has examples of musical tones. Let's go through that. Or we could, if you want, we could give a break and come back, or look at this and maybe just say bye today for, let me see. Let's give a short break then, a 10-minute break. I think that would be fine. Okay. Any questions? Start the recording and share our screen. Let's check a few more motivational slides. These were fun because you can hear, for instance, this is a sinusoid signal. Okay, sinusoidal or sinusoid at a certain frequency. You guys will know how to detect that, of course. This is, for instance, it is oscillating at 523 hertz. Okay, so frequency is how many cycles are in a second, right? And period will be actually the duration of one cycle. So they will be inversely proportional to each other. So F will be 1 over period T, which is T. We show it typically by T. So a simple sound is a single tone, meaning in your guitar, for instance, or in your piano, when you press a single note, like a C, that will be oscillating at a certain frequency like this. So if you do a time frequency graphic like this, it will, you see, show only the duration of the time signal, and for that duration, it's going to show the frequency. So here, you guys hear that, right? So that is the single tone or a musical note at a certain frequency. So you can now change the frequency in time in a piecewise linear fashion. So you see in certain periods of time, for instance, 0.2 seconds, 523 hertz played, for instance, the second 0.2 seconds, 600 hertz signal or tone played, and things like that. So maybe I can play this again. And frequency is increasing. That's the important thing. You can here, I hope, differentiate the difference between this high pitch or high frequency signal and low frequency signal. Pay one more time attention. Yeah. And now you can play a song by, you see, actual synthesizing. You can also synthesize those musical notes because you are just playing a sinusoidal note for a certain duration, right? In your time frequency diagram, you can represent a musical song, I mean a song. So your musical notebooks, right? When you write your notes there, that's a time frequency diagram actually, right? I mean, this is a very old familiar song from your primary school times, probably. So let's see. So yeah, for instance, we can try to change the frequency very abruptly. It says continuously, but just play each note for a very short time and increase the frequency. This is called a chirp signal. Chirp is like a bird's song or bird sound. So you can also make this similar in your mind, see the resemblance to a maybe police siren or something like that. Let's see. Right, police or ambulance. Sirens are also made out of such synthesizers of different songs. Okay, different notes at meaning these musical notes at single frequencies, even more complex signal. Yeah, you can.
This voice has been synthesized by a computer.
So you see, you can, of course, we all know human speech can be synthesized. So I think, let me see here. Just as an example, you guys will learn these in the coming weeks, but for instance, I'm showing two sinusoids, one high frequency, one low frequency. One of them is at 200 hertz, the other is at 20 hertz, and you guys will already notice which one is the smaller frequency. This is the 20 hertz signal, this is the 200 hertz. You can, for instance, multiply them to obtain beat notes. Those are like those disco music. Disco songs that typically they have these beats at the background. We can play one example next time. You will be, the point here is, for instance, multiply those two sinusoids. Actually, we can rewrite this as an addition of two sinusoids, okay? And represent it as a sinusoid with the difference of the frequencies, so 180 hertz plus another sinusoid with the addition of the frequencies 220 hertz, okay? So you can also, of course, show them as really through the multiplication, or you can, when you also add them and display them, it's going to also show in this form. Okay, this is called waveform of a beat note, very typical frequency. Also, this idea is behind amplitude modulation too. We typically take a low frequency signal like our audio signals, our speech signals, and we multiply it by a much higher frequency, carrier frequency. Then we send that multiplied signal, which is called a modulated signal, through a communication channel, and then at the receiver, we actually demodulate by again multiplying with the same sinusoid. And that is the idea of amplitude modulation. You guys will, with the mathematics and the concepts in this course, it will be really very easy and straightforward for you to do these manipulations. And that will be true also something called an Euler formula. We will go to the complex domain, so a little bit complex calculus, but that's very simple for you, not difficult, I mean. When I say simple, students every year make a comment like the professors thinks we are at high school level, but guys, I make these comments sometimes saying this is high school math, you should know this. I don't recall now, but complex calculus, is that new to you, or you've already studied in high school or in the freshman year probably? We will study it next time, so don't worry. All right, I think that might be, so here is some math with the complex calculus actually. But this may look very difficult at this point. Actually, it's good I put it here. It's very simple, you guys will see. We convert the cosines to the real part of a complex sinusoid and do the math, go back to the real sinusoid, okay? Okay, here's an example of a beat note. Here, for instance, it signaled a sine with a 660 hertz and another one at 12 hertz. They were multiplied. So you do the math. I mean, this is the multiplied beat signal. You do the mathematics here. Don't worry, we will do this in the next 1-2 weeks. Oh, the music did not play. Huh. So here, the beat note, you see there is a low frequency and the underlying low frequency and the high frequency component. I hope it's clear, but maybe we can try to find other examples next time. Yeah, I think I have a better demonstration for this. I can show it to you. I think this is a little bit too ahead of the class, but this is a spectrum representation of this signal. You will learn about this. Spectrum representation is really summarizing the frequency content of the signal, okay? So this axis is the frequency, and these are the complex amplitude of that frequency, of each frequency that exists in that signal, okay? Okay, these will be coming next time, don't worry. I think that should be it. Normally at this point, we were going to, like I said, defining the signal, like writing a cosine signal at first and recognizing its parameters like frequency, phase, amplitude. But like I said, we will start next time.